Hello everyone, my name is Serkan Sevilgen, and today I'm gonna present my timbre-driven mapping strategy for digital musical instruments that recouples gesture and sound. We define mapping as the relationship between performer's gesture and resulting sound. In acoustic instruments, this relationship is determined by physical constraints, like bow pressure simultaneously affects volume and timbre, and finger position determines both pitch and spectral characteristics. Multiple concurrent gestures produce varied sonic outcomes through inherent physically determined mappings. On the other hand, in digital instruments, this physical coupling does not exist. For example, our MIDI controller assignments are just arbitrary. There is no inherent relationship between a given controller and a given parameter. The mapping is simple but lacks perceptual coherence. The central constraint is physiological and cognitive, not technological. Humans can manage approximately 3 to 5 concurrent degrees of freedom. Acoustic instruments accommodate this limitation effectively. For example, a violinist employs fingers and bow to produce a broad timbral range. Similarly, wind players use lips, tongue, and fingers. The instrument's internal mapping compensates for the limited control dimensionality. The synthesizer that I'm going to present today as an example of a timbre-driven mapping strategy exposes 57 parameters. With a conventional one-to-one mapping, a performer controlling 3 to 5 parameters leaves 52 to 54 parameters static, or we should find some way to control them. The instrument's potential remains largely inaccessible. The mapping lacks perceptual organization. Here is our approach, a timbre-driven mapping. In this case, the controller navigates timbral possibilities rather than manipulating individual parameters. The synthesizer generates audio samples spanning its parameter space. Each sample is characterized by spectral features. A variational autoencoder compresses these features to 3 dimensions. A multilayer perceptron is trained to predict the 57 synthesizer parameters from these 3 coordinates. During performance, the controller inputs map through the MLP to the synthesizer. Our key properties: adjacent controller positions yield perceptually similar outputs. Continuous controller movement produces continuous timbral change. And the performer develops intuition through oral feedback analogous to acoustic instrument practice. Here is our system pipeline. The upper row represents offline training. Synthesis, corpus generation, feature extraction, variational autoencoder compression, and multilayer perceptron training. The lower row represents real-time performance, controller input, MLP inference, parameter input via OSC, and finally, sound synthesis by Csound instrument. The trained MLP model transfers from the training pipeline to the performance chain. The variational autoencoder is not present in the performance path. It serves only to generate training targets for the MLP. During performance, no encoding or decoding is required. Why are we using those tools? What's the purpose? Variational autoencoder is selected for producing a smooth, continuous latent space where proximity corresponds to perceptual similarity. MLP is selected for inference speed. approximately 1 to 2 milliseconds, and for its deterministic output and absence of sequential dependencies. PyTorch provides dynamic computation graphs for iterative development. Additionally, Torch script enables model export for optimized inference. Csound is an established audio programming language with a modular user-defined opcode architecture, and it receives parameters via OSC, Open Sound Control. The system architecture permits substitution with SuperCollider, Max, Pure Data, or any OSC-capable environment. TUI stands for Terminal User Interface, and it is built with Python and textual library. It operates in a terminal environment without external GUI. It means graphical user interface dependencies, and it displays all 57 parameters concurrently alongside controller slides. Here is our synthesis engine. 4 engines operate concurrently within Csound. Filtered noise bank, 8 bands of filtered noise, 24 parameters, producing textual and density-based timbres. FM cluster, 3 carrier modulator pair with cross feedback, 13 parameters, producing inharmonic and metallic timbres. A wave shaper, hyperbolic tangent distortion with asymmetry and filtering, 6 parameters, producing saturated spectra. And granulator, deterministically scheduled grain class, 8 parameters, producing pointillistic textures. Mixed and global, engine blend weights, pitch and amplitude, 6 parameters, and total 57. We have 2 design constraints. The first one is determinism. Identical parameters yield identical output, which is necessary for corpus validity. And electroacoustic orientation. The timbral vocabulary emphasizes noise, inharmonicity, granularity, and saturation rather than conventional synthesis tones. Our feature descriptors. 5 descriptor categories address distinct perceptual dimensions. MFCC, malfrequency capsular coefficients, characterize the spectral envelope on a perceptual frequency scale. The count exceeds the 13 standard in speech recognition due to the greater spectral complexity of the synthesizer. Spectral centroid quantifies brightness. Spectral flatness distinguishes noise-like from tonal signals, particularly relevant given the synthesizers range from broadband noise to quasi-harmonic FM output. Spectral flux measures the rate of spectral change, reflecting granular density and modulation speed. RMS energy captures amplitude. Each of 29 descriptors are summarized by 5 temporal statistics: mean, standard deviation, minimum, maximum, and delta mean. This yields 145 dimensions per sample. The statistical summarization preserves temporal dynamics without requiring sequential modeling. This is how we generate our corpus, our training set. Latin hypercube sampling provides even coverage of the 57-dimensional parameter space across 100,000 samples. This sampling strategy avoids the coverage gaps, characteristics of random sampling in high-dimensional spaces. Frequency parameters use logarithmic scaling for perceptually uniform distribution. Clips are 0.5 seconds at 44.1 kHz, and almost all of the samples are valid. Feature extraction applies the 29 descriptors with 5 temporal statistics, producing 145 dimensions per sample. Pitch and amplitude are intentionally varied across samples. Fixing them would cause the features to encode pitch and loudness rather than timbral characteristics. Rendering is parallelized across 10 Csound instances. It was pretty fast. This is why one of the reasons that I use Csound. The variational autoencoder compresses 145 dimensional feature vectors to a 3-dimensional latent space. The target dimensionality matches the intended controller configuration. In the scatter plus, you can see that each point represents one of the 100,000 samples colored by global amplitude. The space exhibits uniform distribution without empty regions or parameter-specific clusters. Variance is near unit on all axes, indicating that the variational autoencoder has learned a balanced representation with roughly equal information content per dimension. The absence of single parameter clustering confirms that each latent dimension encodes a mixture of timbral properties rather than corresponding to individual synthesis parameters. Alright, here is our multilayer perceptron prediction results. We have well-predicted parameters, carrier frequencies, filter frequencies, and grain density, global amplitude. These parameters produce direct spectral effects that the feature set can resolve. We have near-chance parameters like per-engine amplitudes, phase, and shape. These are perceptually masked. Their individual contributions to the spectrum are not resolved by the feature set. 25 of 57 parameters operate at chance level. This outcome is consistent with the system's design intent. Parameters that the model cannot predict are those whose individual contribution to the perceived timbre is negligible. They appropriately remain in the background. And for the real-time performance, we have an app. As you can see in the signal chain, the controller sends 3 latent values to the MLP for prediction, which outputs 57 parameters in 1 to 2 milliseconds. Parameters transmit via OSC to Csound for synthesis. No variational autoencoder components are involved. The performance chain consists of a single feed-forward pass. Let's look at the UI of the app for now. On the left panel, there are 3 sliders, one per latent dimension. On the right panel, you can see all 57 parameters displayed in real time, organized by engine. The green indicators denote well-predicted parameters, responsive to slider input. Dim indicators denote near-chance parameters that remain relatively stable. For now, I would like to move to live demo of the performance app. Okay, here is our terminal user interface application. It is in Python, and I'm running it with my MLP model here and my scalars file here, and I'm gonna use my MIDI controller, and I'm defining it here. Okay, here is our performance app, real-time performance app. Here you can see the latent space parameters, 3 variables, and here we have 4 synthesis engines: filtered noise bank, wave shaper, FM cluster, and granulator. And you can see all the parameters that we are gonna predict by changing those latent space variables. And from the green dot and dim dot, you can understand which parameters are well predicted, which are only near chance. And here's the mix part. So we are mixing those 4 synthesis engines, and here are global parameters for pitch and amplitude. As you might get a second later, we don't have separate pitch and amplitude slider or controller. So it is all built in the model. And I'm gonna control everything through those 3 variables. And whenever we move those sliders through our MIDI controller, we will produce 57 parameters in real time, and we will send those values to Csound via OSC at this port. And this is the summary of some global parameters. Without starting sound engine, let me show how this works. So I am going to only move one slider for the first latent variable. As you can see, when I move this single variable, almost all the parameters are changing, because with the new value of the first latent space parameters, we are predicting the all possible synthesis parameters. As you can see here, our pitch and amplitude is also changing. Now I'm starting my sound engine. While playing with this instrument, I have learned that from the experience that if I move the first 2 parameters to maximum and the last one to the minimum, the amplitude is going to 0. So this way I can stop my sound without having a separate volume control. And as you can see here, if I increase the amplitude by employing these changes on these parameters, not only the amplitude changes, but all other timbre related parameters change. Okay, we are coming to the end of this presentation, and those are my conclusions and my next steps. First, the system operates end-to-end from corpus generation through ML, machine learning training, to real-time performance. Second, timbre-driven mapping restores the gesture-sound coupling absent in conventional digital instrument design. Third, the design principle mirrors acoustic instruments, limited control dimensionality, rich timbral output. And my future directions: I would like to expand to a 5-dimensional latent space, 3 timbral dimensions with separate pitch and volume axis, and maybe experiment with other dimensional latent spaces. Let's say a 1-dimensional space to 24-dimensional space. And I'd like to develop additional performance infrastructure, pattern generators, envelopes, reverberation, spatialization, and direct engine mix control to make this tool more musically appealing, and conduct perceptual evaluation studies with performers to assess learnability and expressiveness, and validate generalizability by testing with alternate synthesis engines and controller interfaces. Thank you for listening. You can find my contact information on screen.